half-life problem. If you don't remember the half-life formula, make it your goal to understand that before we move on from this. So you're going to ask questions if you need to about understanding it so you don't have to memorize it. So we have a phosphorus that has a half-life of 14 days. We have 6.6 grams present. I'm going to jump to B. When will there be 1 gram remaining? Well, I can get an integer interval and know the answer to that. Because if I start at 6.6, in 14 days, that's going to reduce to 3.3. In 28 days, that's going to be about 1.6. In 42 days, that's going to be about 0.8. So it's going to be close to 42, but not 42. Doesn't that make sense? So if you do a problem like this and you end up with an answer of 9,000 days, you've made a mistake. If you end up with an answer of 2 days, you've made a mistake. All right, so these problems are pretty easy to understand about what our answer should be. So express the amount of phosphorus remaining as a function of time t. Well, every 14 days I multiply the amount by a half. All right, so after 32 days, now first it says as a function of time. I hope as soon as you see that, you're going to do amount as a function of time. Amount as a function of time equals. Do you have to do that? You don't, but boy, when I see something as a function of time, that is of t. It's a really, really good habit to get into. Okay, so what do I do? What did I do right down here on B? I just took my 6.6 and started multiplying it by a bunch of halves. So I took 6.6 and I multiplied it by a bunch of halves. How many halves? Well, if it's 14 days, I multiply by a half once. 28 days, I multiply twice, etc. How many halves would I multiply if it was just 1 day? I wouldn't multiply by a full half, would I? What fraction would I use? 1/14. Good, Matt. 1/14. So what if it's t days? T/14. Doesn't that make sense? Now when t is 14, I multiply by a full half. When it's 28, I multiply by a full 1/2 2 times. When it's 1 day, only 1/14 of multiplication by 1/2. It's a formula that I hope would make sense. Okay. So when B asks, when will there be 1 gram remaining, I want 1 equals 6.6 times 1/2 to the t on 14. To solve this for t, I'm going to have to get that variable out of the exponent. I'm going to have to use logs. Am I ready to? The exponential portion is that. I need to divide 6.6. If you have an 84 or beyond, you can now do log of choose your own base. What base would you use? Easy. What base are we working with? Yeah, half. We'd use base 1/2, and I would get log base 1/2 of 1 on 6.6 equals t on 14. Multiply by 14 and we got it. But I'm going to do this as if you did not have, or I do this as if you're working with an 83. So I'm going to take ln of both sides, and I get ln 1 on 6.6 equals t on 14 times ln 1/2. If I want to solve for t, 14 is just a number. T divided by 14, I'm going to multiply by 14 to get it out of there. ln 1/2 is just a number. I'm not dividing by 1/2, I'm dividing by all of ln 1/2. So that does it for us. Again, I would hope those of you with 84s or beyond would just take log base 1/2 of both sides here, and we would have gotten what? Log base 1/2 of 1 on 6.6 equals t on 14, or there is a viable solution as well. Again, this is one, if we do it and we round our answers and we work this out, we know integer values that we should fall between. We should be able to make some sense out of half-life problems. Let me see, show of hands if you feel like, you know what, I do. I really, really do understand the half-life formula. It makes sense why this is t on 14. If it doesn't, I want you to talk with me, and I will make that make sense to you. Okay, number 6. Determine how much time is required for an investment to double in value if interest is earned at 6.25% compounded quarterly. That doesn't mean every 3 months I get 6.25%. Here's another formula I believe should make sense. The one we might not make sense out of is continuous. Amount equals P e to the RT. But compoundings should make sense to us. So I'm going to, how much time will it require an investment to double? $1 million turns into $2 million, or $1 turns into 2. I end up with 2. I start with 1. 1 plus. When I distribute the 1, that just means I get my $1 back. If this was $1 million, when I distribute to the 1, I get my $1 million back. And now let's handle the interest that I get each compounding. I don't get 6.25%. I get that for the year. But that's divided over 4 different time periods. So I don't get all of 0.0625. I get 0.0625 in this case divided by 4. Any questions on that little portion of it? The parenthesis portion. If I leave this investment in for 10 years, this doesn't happen 10 times. This happens 40 times. 4 times every year, right? So 4 times the number of years. If this is monthly, this is 12, this is 12. Does that make sense? What's the 1 for? We get our money back. Everything after that is our interest. Okay, so at this point, truthfully, I am ready for LN. If I had to put my $1 million in here and this $2 million, I'd need to divide first. But I'm ready for LN right now. Or go ahead, be my guest. You got an 84? Let's do log base that mess, which I'm going to call star from this point forward. If I reuse that mess in just a moment here, I'm going to just LN both sides. So I get ln2 equals 4t. I'm going to ask you this. When you're making t's in here, because we're going to be going into parametrics quite a bit where you use t, if you would, try to get in the habit of putting a little curly on the end. Otherwise it starts looking like a plus. It becomes a real challenge to grade sometimes. So times 1 plus 0.0625 on 4. And now if I'm solving for t, 4 is just a number. Got to divide it. This is just a number. This is, I'm sorry. Still got an ln in here. I'm sorry. You see it? Still got an ln in there. ln of this is just a number. ln 1 plus 0.0625 on 4. Is that okay? All right. Had I done log of this, which I'm going to call star, I'm going to say this is star, then I would get log base star, that ugly base, equals 4t. So t is just log base star on 4. You could do that on your calculators. You could enter it exactly as it appears here for your base. Any questions there? Okay. I can actually edit that out. Okay, very good. Let's go ahead and grab 4. I think I'm going to grab 4. Thank you. Okay. I'm going to show you a little something different on 4 today. This problem right here, I want to come back. We're going to come back and talk about this a little bit today. It's a lot like your problem number 8. I don't care if on your problem number 8 you just get the graph off of your calculator. You've got a secant tangent one there. This one actually turns into half a hyperbola. I think your secant tangent problem might be a parabola, but we're going to come back and talk about that at a different time. So let's skip that one for right now. And your number 8, you can just graph it straight from your calculator. All right. Now, when we were talking about this problem yesterday, I'm going to start over again. When we were talking about this problem yesterday, I said, I believe it's a circle. Remember? I said, maybe it's a parabola. There's ways for us to know that ahead of time. I can do what's called, and we did some of it last year, eliminate the parameter. Now I'm going to start with the simpler one, eliminating the parameter. If we go to our example 5, I've got 2t minus 5 is x, and I've got 4t minus 7 is y. I could go ahead and do this parametrically, graph it, and analyze the graph and say, I think it's a line. But knowing it's a line is pretty easy. Knowing it's a circle, not necessarily easy by looking at it. What if it's an ellipse? What if it's not either of those and it just kind of is circular in nature? So what we can do is we can eliminate a parameter. For instance, if I solve this for t, I get t equals, I started with x, I have to add 5 across, and I have to divide 2. We live in XY land. We don't live in XYT land. I mean, our past is ensconced in XY. That's where we're comfortable. I'm not comfortable with this t here. If only there was some way to replace this t. I got a replacement for it. Y equals 4 times x plus 5 on 2 minus 7. So y equals, this reduces to 2x plus 10 minus 7 plus 3. Let's jump down to number 6 just for a moment. X equals 4 minus root t, y equals root t. I'm not even going to solve for t. Root t is y. Oh, this is x equals 4 minus y. Which, if you like, is y equals negative x plus 4. Add y, subtract x. We don't have to guess anymore. We don't have to analyze the graph. We just replace the or eliminate the parameter. Okay, let's go back to this though. Now we're going to go through the parametric graphing. So I am going to choose t, find x, find y. T can be anywhere from negative infinity to infinity. What's that tell me about initial point, terminal point?
There is none.
There, we have none, right? Initial point, terminal point, we don't have any. It's going to go forever. That's some of the things that are being asked here. So I'm going to pick t. I think I'm just going to start at 0. I might want to go into some negatives. Let's just see how it goes. I put in 0. I get negative 5. I put in 0. I get negative 7. And we'll build from there. I put in 1. I get negative 3. I put in 1. I get negative 3. Is that okay? I put in 2. I get 4 minus 5, negative 1. I put in 2, I get 8 minus 7, positive 1. And I notice something. I'm going up 2, up 2. Do I expect it to continue to go up 2? Sure, that's linear. Slope 2. I'm going to get 2 bigger each time. So if I go to 3, I'm going to be up at 1. I go up 4, I'm going to be at 5. That's probably enough. If the x's are changing at the same rate all the time and the y's are changing at the same rate all the time, my graph's going to be a line. Let's graph it. I need x's that are primarily negative, y's that are a mixture. So I've got negative 1, 2, 3, 4, 5, y's 1, 2, 3, 4, 5, 6, 7, and y's up to 1, 2, 3, 4, 5, and x is over to 1. Negative 5, negative 7, negative 3, negative 3, negative 1, 1, and 1, 5. More than I need after I decided that it was linear. Now, I didn't hit 3 here, but of course I'm not working with a straight edge or with graph paper. Let's see. If I go up, what was it? Up 4 over 2, up 4 over 2. From here, if I go up 2 over 1, sure enough, I would hit that. I do have the line y equals 2x plus 3. I can figure out the Cartesian equation before I ever do the graph. Is that all right? And we can do that with sines and cosines. If I went back, let's say, this is just some scratch work page, just watch this. Let's say this instead was x equals sine of, let's do this, x equals cosine of t and y equals sine of t. I want to eliminate t. Bit of a challenge. But what if I squared this equation, added these equations together, this plus this equals, does that ring a bell? X plus, yeah, x squared plus y squared equals 1. Oh yeah, this can be a circle. Right, remember, is that kind of coming back to you a little bit? We eliminated parameters last year. Okay. All right. We did a tiny bit of this. We may have never used the term parametrization last year. Here we've got a line segment that passes through these 2 points. You have to pay real close attention because this confused people a few people throughout the day. We want to write that as parametrics, but it's a segment. So I go from negative 1 to 4 as I go from negative 3 to 1. I can write this as x equals, what does x start as? Negative 1. And then where does it go? It goes, in this case, from negative 1 to 4, it increased by 5. In some time unit. And in that same time unit, y went from negative 3 up to 4, so it increased by 4 in the same time unit. What's the time unit? I don't know. 11 seconds is the time unit. I don't know. So in that case, t, one time unit, stands for 11 seconds. Or what I could do is I could find the midpoint of these and say, well, we only go from negative 1 up 2.5 in a time unit. And then I'd need 2 time units to get here. But why not just say 1 time unit gets us from here to there? So it gets us from negative 1, negative 3, up to, it wouldn't go through the origin, up to 4, 1. And I don't want to go any further than that. So tell me about the values of t. T is clearly not negative infinity to infinity, because if t was negative 6, I'd be at negative 31, negative 27. What values of t keep us on this segment? T's got to be at least 0. 0 puts me right here at the initial point. And I said this is 1 time unit. So it's not two values, 0 and 1. It's 0 and all the values between 0 and 1. If I allow, let's say I allow t to be 1/2. I start here, x goes over 2.5, y goes up 2. Is that all right? But then I allow x to go all the way up to 1. We fill in the rest. So the question should be, well, if I'm doing a segment like this, should it always just be 0 to 1? I'd make it 0 to 1. I could make it 0 to 10, but then I'd have to change 5 and 4. Instead of 5, this would be 5 divided by 10. 4 divided by 10. Why would we want to do that? Why wouldn't we just want to say it's one time unit? Is that okay? I put in point 1, it's going to just advance, put in point 2, put in point 3, it's just going to advance me along that segment. Once I put in 1, I've made it to here, and I'm done. That's what controls how far we go. Let's do another one similar to that. Let's jump down to C. Array. I'm going to go ahead and start with a sketch of this. I don't know if that helps. I hope so. So we're at 2, 3. The ray passes through -1, -1, and goes forever. So I'm starting at 2, 3. So x starts at 2, y starts at 3. And then where do we go from there? I go left and down. How far left and down? Well, eyes up here. I could go this far left and down and figure out what that point is. Or I could go this far, figure out what that point is. I could go this far, figure out what that point is. But why wouldn't I just say, let's just go this far and that far? I just need a target to pass through. Bow and arrow. I need a starting point and a target to shoot through. So what does my x do? It goes from 2 to -1. It goes down 3. Eventually, maybe in 3 seconds, maybe in 11 seconds, maybe in 40 days. But whatever it takes, however long it takes me to get there, I'm just going to call that a time unit. What does y do? It goes from 3 to -1. It goes down 4. In that same number of time units, maybe 11 days. Okay? What's the fundamental difference, though, between this and this? Yep. It just keeps going. Okay, notice, when t is 0, I get this point. As t gets bigger, I get to here. But I want to get bigger and bigger and bigger. It's a ray. So t is bigger than or equal to 0. Questions there? I'd like to answer them if you got them. Okay. All right. Let me see hands if you can tell me why this question makes no sense. We're supposed to find the parametrization of the lower half of the parabola y equals x squared plus 2x. Matt?
X squared parabolas, there is no lower half. There's not parabola.
Yeah. X squared, very good, very good. X squared parabolas open up and down. This one happens to open up. Well, what the heck is the lower half of that? Do they mean under the x-axis? That's not half of the parabola. This shouldn't be lower. This should be left. The left half. If this was y squared plus 2y, problem makes sense. Okay. Yep. Thank you. Thank you. Wonder if that just showed up on the video. We'll see. Okay. All right. So this is going to seem really weird. The question is going to be, why are we even doing it? I'm going to give you a little hint to why we do this, and then there'll be, as the course moves on, you'll see why we want this as parametric versus Cartesian. If we have a function that's solved for y, really simple. If it's not solved for y, we want to solve it for y. Once it's solved for y, I'm just going to say x equals t. This is my parametrics. What do you suppose I'm going to say y equals now? Since x equals t. T squared plus 2t. All right? Now, I'm going to go ahead and sketch the graph of this, not from the parametrics, but from y equals x squared plus 2x. I do know that's x plus 2 times x. If I set that equal to 0, I learn my zeros real quickly. I've got zeros at 0 and negative 2. Therefore, my vertex is when x equals negative 1. And I got two pretty good ways to figure out where my y-coordinate is. I can put negative 1 in here. Or I can say, since this is 1x squared, this parabola opens upward at the normal rate. So if it opens upward, it looks like this. At the normal rate would be over 1 up 1. Oh, this is down at negative 1. But I am only interested in the left half of that parabola. Okay. Watch what happens here when t is 0. When t is 0, I get 0, 0. That's not what I want. When t is negative 1, well, think about it. What did I do? I said x is t. This might as well just be the t-axis now. If x is the same as t, what do I want t to be? I want t to be negative 1, because what do I want x to be? Negative 1. So t is going to be defined by negative 1. Now, don't think in terms of this is going left, normally, because the x is going left, that we want to be less than negative 1. What would get us here? That's our negative 2, get out 0. We are moving left because now x is t. So as soon as I see this, I'm like, well, I want x to be less than negative 1. Therefore, t should be less than negative 1. Or t is less than or equal to negative 1. And you're like, why did we even bother and just not leave this x here and change that into x? It's a really good question, but this is a nice way to, with parametrics, to just lop the graph in half. We equivalently could have said this is x squared plus 2x, but x is less than or equal to negative 1. They're the same. Okay. We'll reveal more along as we move about why we might want to do this. Okay? Questions there?